For problem 2, we have a water substance with an absolute pressure of 1 bar and a quality of 0.25 at state 1, and it's expanded in a closed piston cylinder device along a path for which PV to the 1.5 is equal to a constant until the absolute pressure drops to 0.5 bar at state 2. So this is a multi-part problem. I'm just going to focus on part A for this first part of the video, which asks us to find the final quality and report our answer in percentage. So for a lot of these longer multi-part problems, it's going to give us a block like this where it asks us to basically just set up the problem first. So we want to identify the system, show the mass and energy interactions in the EFD, list any assumptions in basic equations, and then we get to providing our solution. So I'm going to spend some time doing that here and just setting up the problem. If you want to skip ahead to the solution, feel free to do so. But if you're unsure about your work or want to see how I set it up, then feel free to stay and watch. So the first thing I like to do before we even get to the system or assumptions or equations is to make this little table here where I just list all of the properties that were given in the problem statement. And it might not be the most relevant thing for this problem, but it's a really good habit to get into because it'll be really useful for us when we get to more complex problems with things like cycles in the future, where we have a ton of variables that we need to keep track of. So the way that I do this is I look at which properties we are given in the problem statement, and I see it gives us some information about pressure, both at state 1 and at state 2. So I'm going to write a column for pressure here in bar, and we see that we start with a pressure of 1 bar, and then we get to a pressure of 0.5 bar at state 2. And then the only other information we're given explicitly from this problem statement is that we start with a quality of 0.25, which we usually write as x, and it doesn't have any units. But we start with a quality of 0.25, and then we don't know what the final quality of the system is yet, but that is what the first part of the problem is asking us to do, so we'll get there. So now that we have everything laid out in our table, we can draw our system and draw the energy flow diagram for that. And so we know that we have some piston cylinder system, the problem tells us, and you can draw it sideways or vertically or however you want. If they told us that we have some changes in potential energy or that the piston had some mass or went through some change in height, then we would want to draw it vertically. But if it doesn't give us anything like that, then we can draw it however we want. And the system that we want to focus on in this case is going to be the water substance that is inside of that piston cylinder device. So now we need to identify for this water substance that we're treating as our system, how is it going to interact with the surroundings, which is the piston cylinder device. And so we need to think about work and we need to think about heat transfer. So for work, hopefully it's pretty easy to see. This water has some pressure. We're not doing any work on it, but it wants to push out against the walls on each side. And these walls on these sides can't move, but the piston itself can move. So it's going to do some work to move that piston to the right as we have it drawn. So I'm going to draw my work term going out of the system because it's going to try to do work to move this piston to the right to a new location. And then for heat transfer, if it told us that this piston cylinder device was well insulated or something like that, then we could say that the heat transfer would be equal to 0. But it doesn't say that, so this water is going to lose some heat as this process occurs. So I'm going to draw my heat transfer going out of the system. If we were doing some external heating to the water, then we could draw this arrow going into the system, but it's just going to lose some heat, so I'm going to draw it going out. So now we can move on to our assumptions, since that's all we have in our energy flow diagram. One assumption that I see right in the problem statement is that it tells us that we have a closed piston cylinder device. So we're assuming that this is a closed system, and what that means for us is that the mass at state 1 is equal to the mass at state 2. The mass is constant the entire time. The amount of water substance that we have here is going to stay the same. Another good assumption to make for most piston cylinder problems is that we have a quasi-equilibrium process. So what quasi-equilibrium means for us is that we basically have uniform properties all throughout this water substance. So the pressure here, for instance, we can assume is the same as the pressure in the middle. It's the same everywhere in here. Same as the temperature is the same at all points and all of that. And so as we move this piston to the right, we're going to have a new volume that would look maybe something like this. And we're assuming that this is a slow enough process that even as we get to a state right here, the pressure here is the same as the pressure here. The pressure throughout this entire thing is uniform. And that's what quasi-equilibrium means for us. We're just able to say that the water substance has one value that we report for pressure, for temperature, the entire time. And it's always in a state of equilibrium because it's a slow process. Another assumption, we are not given any information about any velocity of the fluid or any change in height of the fluid or anything like that. So it doesn't say anything about any kinetic or potential energy. So I'm going to say that the changes in kinetic and potential energy are just going to be equal to 0. And the last thing I notice about this problem is that we can say that we are neglecting any friction between the piston and the cylinder that houses it. So we can say that this piston, as it moves, it's not going to be rubbing against the walls of the cylinder at all, which would really affect the work that we're able to get out of the system. And it doesn't give us anything about friction coefficients or anything like that, so we can just neglect that friction. Okay, that seems like a good list for now. And then we'll move on to equations. And I'll just take the equations that we're going to need for part A, which is just finding the quality. So to find the quality, I think we're going to need the equation that we have for quality from our equation sheet. So I'll scroll down so that we can look at that. So here, the equation that I have underlined is the one that we use for quality. X is our variable for quality, and we know Z is just any property that we want from our tables, pretty much. And these ZG and ZF are given values that we can find from the table. So I'm going to come up and write that equation up here. So we have Z for a mixture is equal to X times ZG plus 1 minus X times ZF. And this should be the main equation that we will need for part A. Okay, so I'm going to go ahead and stop the problem setup here, and then I'll move on to the solution. Okay, now let's move on to our solution for part A, which again is asking us to find the final quality, which is this value from our table here, x2. So to solve for x2, how do we actually do that? Well, let's look at our equation that involves x. We want to solve for x2 using this equation, and it looks like we have a lot of unknowns, but actually we need to remember that ZG and ZF are actually known values from the table as long as we know the pressure at that state. So if we go down here and we look at the table, at 0.5 bar, which is what we have for our state 2, all of these are the potential values for ZF, and then all of these are the potential values for ZG. So we have those known, and if we want to solve for x2, all we have to do is just find Z mix at state 2. So I'm just going to write that down real quick. If we want x2, all we need to do is find Z mix at state 2. But then the next question is, what value should we use for Z? We have some different options. We can really use any of these values for our Z, any of these properties. But if we remember, in the problem statement, it tells us that we have this relationship, PV to the 1.5 is equal to a constant, this polytropic process relationship. So what does that mean mathematically for us? Well, if we write that out, that means that this PV to the 1.5 is the same at state 1 that it is for state 2. So that means that P1 times V1 to the 1.5 is equal to P2 times V2 to the 1.5. And look at our table. We already have the values for P1 and P2. So if we can just find the specific volume at state 1, we can use this equation to find the specific volume at V2. And that is our Z mix 2 value that we can use to find our final quality. So that's going to be our solution. We're going to use specific volume with this equation, and we're also going to utilize our polytropic process relationship. So let's solve. So again, the first step will be to find V1, and we can do that using this equation up here. V1 is equal to x1 times Vg at state 1 plus 1 minus x1 times, Vf. Again, we're just plugging in V for Z here. And these values we can get from our table down here. So Vg is going to be our specific volume at 1 bar here because we're at 1 bar at state 1. And then Vf is going to be our specific volume at 1 bar for the fluid side. So we plug in those values and we get 0.25 times Vg, which is 1.6939 meters cubed per kilogram. And we add 1 minus 0.25 times this value here, which is 0.0101432 meters cubed per kilogram. And this should evaluate, if you plug it into your calculator, to 0.424 meters cubed per kilogram. Great. So now let's just move down to the next page here, but I will copy this down. Give ourselves some more space. Now again, we're going to use our polytropic process relationship that we have, P1 times V1, and this time I'm going to write 3/2 instead of 1.5 because it might make just writing out the math a little bit easier. But that's equal to P2 times V2 to the 3/2. And now we want to solve for V2. So if we rearrange this, we're going to say V2 is equal to, we bring P2 over to the other side, so P1 over P2 times V1 to the 3/2, and then all of this we are going to raise to the 2/3. So see, I'm moving the P2 over to the other side, and then to undo this 3/2, we multiply everything by the inverse, or raise everything to the inverse rather, to the 2/3. So this is going to evaluate to P1 over P2. We can use the ratio still in bar here because the ratio in bar is going to be the same as the ratio in pascals or PSI or whatever standard unit you want to use. So we can keep it in bar, which is kind of nice here. So we get 1 bar over 0.5 bar times V1, which is 0.424 meters cubed per kilogram. And then, that's raised to the 3/2. And then everything is raised to the 2/3. And if you evaluate that in your calculator, you should get V2 is equal to 0.673 meters cubed per kilogram, or at least something close to that. Okay, great. Now we have V1 and V2. The last step is to solve for the quality x2. And we're going to do that using, again, this relationship, but it's in kind of a complicated form because we have x appearing twice here. And so maybe there's a simpler form that you have memorized, but if not, I'll just show you how to get there from this equation. We just need to do some algebra to rearrange our variables. So, writing out the equation, we have V2 is equal to x times Vg plus 1 minus x, this is going to be x2 as well, x2 times Vf at state 2. So to rearrange this, we just need to distribute our Vf into these parentheses. This is going to be x2 times Vg plus Vf minus x2 times Vf. And then we want to rearrange this so that the x2's are together. So to do that, we subtract the Vf over to the other side. So then we get V2 minus Vf is equal to x, and then we can group together Vg minus Vf. And so the final form of this equation is x2 is equal to V2 minus Vf over Vg minus Vf. So maybe that's the form that you have memorized, but if not, you can get there pretty quickly from the version that you see on the equation sheet. So then V2 we found again to be this 0.673 meters cubed per kilogram. And then we subtract off. Now we need the values from the table at 0.5 bar because that's our ending pressure. So this is Vf and this is Vg now. So we're subtracting off Vf first, which is 0.0010299, 0.0010299 meters cubed per kilogram. And all of this is divided by our value for Vg, which is 3.24. You see here. 3.24 meters cubed per kilogram minus the same thing, 0.0010299 meters cubed per kilogram. And that should evaluate to x2 equal to 0.208, or they told us to write it in percentage, so x2 equals 20.8%. So that should be our final answer. X is equal to 20.8. Okay, now we'll move on to part B of this problem. And before we do, I have the same setup here that I had for part A, except for my table now, I've added in these values here in red, which we found from part A. So we found the final quality at state 2, and we also found these values for specific volume at both states 1 and state 2, which helped us to find the quality. This is another reason that it's useful to use a table, because these values are actually going to be useful for us as we work on our answer for problem B. So it's nice to have everything just laid out here because you never know what's going to be useful for future problems. But now we'll move on to part B, which asks us to calculate the work per unit mass of water during the process and to report our answer in kilojoules per kilogram. So remember, work per unit mass, kilojoules per kilogram, that tells us that we're finding specific work rather than total work. So we need to figure out what this W out arrow is and figure out what kind of work it is to start. We need to determine what kind of work this water substance is capable of doing. So let's scroll down to our equation sheet real quick and determine what that will be. Remember, we have all of our possible values for work here, but we don't have any electrical work or any springs or any rotation of any shafts or anything like that. So the only work that we're going to be focusing on is the boundary work, or the PDV work that the water is doing on the piston. So as this water moves this piston to the side because of its pressure, the volume is going to change, and that will be our boundary work, or our PDV work that we see here. And just a quick note on the version of this equation that you see here. This gives us a capital W and a capital DV version, which is the total work and the total volume. And so this will give us an answer in terms of energy, like joules or kilojoules or something like that. But remember, they ask us to find the specific work, so we can use the lowercase version of this equation, where little w is equal to pressure with respect to specific volume, little v. And this will give us an answer in terms of joules per kilogram, or kilojoules per kilogram, or some energy per mass. So this is the version that we are going to want to use because it'll be convenient for us. So I'm going to write that equation down here, the work, and in our case it's the only work from 1 to 2. So we'll just say work from 1 to 2 is equal to V1 to V2 of pressure with respect to specific volume. And in some problems that you see, it'll tell you that it's a constant pressure process. And in those cases, this equation is really nice because if the pressure is constant with the changing volume, we can move the pressure out front and just calculate basically the pressure times the change in volume here. But this is not the case for us here because we see that pressure is changing from state 1 to state 2 as volume changes. So pressure is a function of volume. And what is that function? Well, remember we have this equation, PV to the 1.5 is equal to a constant. So in order to evaluate this integral here, we need some version of pressure that has specific volume in it. And we can get that from this equation. We can just move specific volume over to the other side and find that equation for pressure. So that's the approach we're going to take. And so I'll start out here just by writing out our work. Again, that's going to be equal to the integral from V1 to V2 of pressure with respect to specific volume. And remember, we want to rearrange this PV equation. So PV to the 1.5 is equal to a constant. I'm just going to call that constant C here because it'll make our algebra a bit easier. So to rearrange this, we can just say pressure is equal to that constant C divided by specific volume to the 1.5. And so now we can write a new equation for work, substituting that pressure in. Work from 1 to 2 is equal to the integral from V1 to V2 of C over V to the 1.5 with respect to specific volume. So I just plugged in this P into that equation. Okay, now we can simplify this a little bit. We can actually take that constant C out of the integral because it is a constant. So now we're going to be integrating from V1 to V2, and I'm going to write this as V to the negative 1.5 dV, which is the same thing as 1 over V to the 1.5, because this is a little bit easier to think about, at least for me, when I'm doing integrals. And we can actually evaluate this. So this will be C times V to the negative 0.5, because we add 1 to the exponent. And remember, we need to take this exponent and put it down and divide by it in front. So we divide by a negative 0.5. And that will be evaluated from V1 to V2. So if we write that out, we just get we'll do negative C over 0.5 times V2 to the negative 0.5 minus V1 to the negative 0.5. So this is our equation, and we're almost there. We know V2 and V1. Remember, from our table, we have those values right here. But we just need to find an expression for C. And to do that, we can just use this equation and evaluate this constant at any state. So if we choose state 1, we can evaluate P1 and V1. Or if we choose state 2, we can do P2 and V2. So I'm just going to choose P1 and V1 and plug that in for C. So we'll get our work from 1 to 2 is equal to P1 times V1 to the 1.5 over, this is a negative over 0.5 from this equation here. I'm just plugging in for C, times V2 to the negative 0.5 minus V1 to the negative 0.5. And so plugging in our numbers, we get a negative P1 here is 1 bar. But we don't want to use bar here. We want to use a standard unit. So remember, we have in our equation sheet some conversions. 1 bar is just equal to 10 to the 5 newtons per meter squared, which is the same as a Pascal. So 10 to the 5 pascals for a bar. So we'll write 10 to the 5 pascals times V1, which is right here, this 0.424. meters cubed per kilogram. That is raised to the 1.5. All this is divided by 0.5. And then we're multiplying this by V2, which is 0.673, to the negative 0.5 minus V1, which again is 0.424, to the negative 0.5. And I forgot to write, but those are in meters cubed per kilogram would be the units here. And so when we evaluate all this, make sure you check your units, but you should get the final answer of the specific work from 1 to 2 is equal to 17.5 kilojoules per kilogram. Okay, now we're moving on to part C of the problem, which asks us to determine the heat transfer per unit mass of water during the process and to report our answer in kilojoules per kilogram. So if you're feeling a little stuck getting started with this part, I'll give you a little tip to use. If you're ever asked to find work in an earlier part of the problem, and then they're asking you to find heat transfer, the chances are you're probably going to be using first law, because first law is the equation that relates work with heat transfer with changes in energy of the system. So if you see work in an earlier part and then you see heat transfer, you should immediately be asking yourself, can I apply first law to this part in order to solve? So let's scroll down to our equation sheet and look at first law to see if we can apply it here. So again, this is the differential version of first law that we have, but the problem tells us that we have a closed system, which helps us simplify this equation a lot because the mass flow into the system for a closed system is 0, and so is the mass flow out of the system. And so if we just integrate both sides of this, if we integrate all of the terms here, then the dots go away and the ddt goes away, and we can get a total form of the equation, which is the total change in energy of the system is going to be equal to the total heat transfer minus the total work. And remember, in the last part of the problem, we are looking at this equation here, this PDV work equation, and it gives us a capital W and a capital dV, but we are able to simplify it to a lowercase w and a lowercase dV just by dividing everything by the mass of the system. And that's useful for us to do again here because they're asking us to find the specific heat transfer, not the total heat transfer. So if we just divide both sides here by the mass of the system, then we are left with the specific form of the equation, which is the change in specific energy of the system is equal to the specific heat transfer minus the specific work. And then we can go one step further to simplify this by remembering that the change in specific energy is equal to the change in specific internal energy plus the change in specific kinetic energy plus the change in specific potential energy. But remember, we are assuming that we can simplify by neglecting kinetic and potential energy because it doesn't give us any information about those terms. So now we're just left with the change in specific internal energy is the total change in energy of the system. So now we can write this equation up in our equation section. So I will go do that. So we have the change in specific internal energy is equal to the heat transfer, which is positive if it's going into the system, minus the work, which is positive if it's going out of the system. So this is the equation that we're going to be using to solve. So I'll just start to write it down in the solution here. And instead of writing delta, I will write the change from state 2 to state 1. U2 minus U1 is equal to Q from 1 to 2 minus the work from 1 to 2. And since we want to solve for heat transfer, I'll just move this term over to the other side. So we get Q from 1 to 2 is equal to U2 minus U1 plus W from 1 to 2. And so we found this work term with the last part of the problem here. So we just need to find U2 and U1 in order to solve this. And remember, those are actually pretty easy to find as long as we have the quality at both states. So since we have the quality at states 1 and state 2, we can actually use this equation that we used earlier in the problem, but instead of subbing in specific volume here, we can just sub in specific internal energy. So I'll write that equation down here. To find the specific internal energy at some mixed state, it's going to be equal to the quality times the specific internal energy at the saturated vapor phase plus 1 minus the quality times the specific internal energy at the saturated liquid phase. So we just need to get these UG and UF values in order to get the specific internal energy at states 1 and states 2. And we can do that just by taking them from the tables. So let's scroll down to the tables here. Remember, since we're in the SLVM range and we know the pressure, we can just use these tables organized by pressure here. So at state 1, we have 1 bar, and at state 2, we have 0.5 bar. So these are going to be the values that we care about here, just these ones in the tables. So we can just write down the values that we care about. So the UF at state 1 is going to be this value here for 17.4 kilojoules per kilogram. And then UF at state 2, remember it drops to 0.5 bar, so then we have 340.49 kilojoules per kilogram. And then on the other side, we have our saturated vapor phase. So UG1 is going to be this value, 2505.6 kilojoules per kilogram. And then UG2 is just going to be 2483.2 kilojoules per kilogram. And now we can just plug these into the equations that we have and solve. So I'll scroll up here. Now we will have U at state 1 is equal to the quality at state 1, which is 0.25. Remember from our table up here, this is our x1, this is our x2. Times UG1, which remember down here is just this value, 2505.6 kilojoules per kilogram, plus 1 minus the quality, times UF, which is this value right here, 417.4 kilojoules per kilogram. And if you do this, you should get 939.5 kilojoules per kilogram. And then we can do the same thing to solve for the specific internal energy at state 2. So we need x2, which is 0.208, times the UG at state 2, which is this 2483.2 kilojoules per kilogram, plus 1 minus the quality of 0.208, times this UF2, which is 340.49 kilojoules per kilogram. And then this should evaluate to 786.2 kilojoules per kilogram. So now we have everything that we need. We have U2, we have U1, and work from 1 to 2. So we can just simply plug those values in here to solve for the specific heat transfer from 1 to 2. So U2 here is 786.2 kilojoules per kilogram, minus the specific internal energy at state 1, which is this 939.5 kilojoules per kilogram, plus the work from 1 to 2, which up here is this 17.5 kilojoules per kilogram. And so if you just plug this into your calculator, you should get the total heat transfer from 1 to 2 is equal to negative 136 kilojoules per kilogram. So this will be our final answer here. And then when we get our final answer, we just want to make sure we can check our sign and make sure it makes sense. So we get a negative value here. And what does that mean? Well, if we scroll up to our equation, we have it so that if Q is in, it's positive. So if we get a positive value here, that would mean that we were drawing our arrow like this. But since we get a negative value, we know that means that we have heat transfer leaving the system, which is exactly what we would expect. This is how we have it drawn. So since we have a negative value, it's heat transfer leaving the system, which makes sense for us here. So this will be our final answer. Now we can move on to the final part of the problem, which asks us to show the process on a PV diagram relative to the vapor dome and the lines of constant temperature for the two states. And they want us to label the axes, the two states, and indicate the process direction with an arrow. So since we know we are going to be drawing a PV diagram, I think it's useful to just first lay out how does pressure change from state 1 to state 2, and how does specific volume change from state 1 to state 2. So pressure here we see we start at 1 bar and drop to 0.5 bar. So pressure is going to decrease as we move from 1 to 2. And specific volume is the opposite. So we're going to start at a lower value and move to a higher value as we move from 1 to 2. So specific volume is going to increase. And just kind of laying this out is useful because we can visualize where the points will be before we even get into drawing any lines or anything like that. So I'll scroll down. I have a PV diagram already set up here, but we'll have pressure on the y-axis and specific volume on the x-axis here. And then the vapor dome will look something like this. And so we already said we know pressure is going to decrease, so we're going to be moving down on the graph. And specific volume is going to increase, so we're going to be moving to the right on the graph. So as we go from state 1 to state 2, we'll start at some point that's up and to the left, and then we will go to some point that is down and to the right. And the exact location where you draw these points isn't necessarily crucial. What is crucial is that you show the changes in an accurate way and show the directions that things change. So that's the important part here. So now we can actually start to fill in some values. So we know that pressure is going to start at 1 bar and then drop to 0.5 bar. So again, these can be kind of arbitrary points that you draw on your graph here, but as long as you show that we are decreasing in pressure from 1 up here at state 1 to 0.5, then that's important. And specific volume will start at 0.424, so maybe that's somewhere around here. And then we will finish at 0.673. Again, just pulling those values from the table here. And so we already have enough to sketch our points, but one of the other things that it asks us to do is to draw in the lines of constant temperature for the two states. So we know that on the PV diagram, we have isotherms, and these isotherms are going to have some constant temperature they're going to be flat lines under the dome like we see here, but then they're going to curve down and to the right coming in and then curve out a bit more flatly like this. And so we'll have two different isotherms at states 1 and states 2. And how do we actually find the temperature value here? Well, this value here is what you actually see in your tables. This gives you some constant pressure and temperature for every point along these lines down in the table. So we can see that right here. For state 1, we're at a constant pressure, but we're also at a constant temperature of 99.61 degrees. So that means everywhere along this line at state 1 is at the same temperature of 99.61 degrees. So we will just draw that in. T1 equals 99.61 degrees Celsius. And then the other one, along this isotherm, we are going to be at whatever temperature we find in the table for 0.5 bar. So that is going to be right here, this temperature of 81.32. So that's our T2. 81.32. degrees Celsius. And now we can actually draw in our points on these lines. So wherever these two intersect, we will be at our point 1. So we'll call this point 1. And then wherever these two intersect here, we'll be at our point 2. Okay, so this point up here is state 1. This point up down here is state 2. So now we just need to figure out what the line looks like to connect these 2 points. And the way that we are able to figure out the shape of that line is from the equation that they give us for the polytropic process. So we see here that PV to the 1.5 is equal to a constant. And typically this equation is written, if they don't give us an exponent here, then we'll write it as PV to the n is equal to a constant. And the shape of the line is just determined by the sign of the n here. So if n is greater than 0, which it is in our case, we see here that it's 1.5, then the line will look something like this. It'll have kind of a downward curve that goes like that. And that's just kind of because of the equation for this line. If you wanted, you can plug P equals C over V to the N into your graphing calculator or something like that to see what the shape of that line looks like, but it's just going to go down and to the right. And then if N was equal to 0, well then this would be V to the 0, so that would just cancel and be 1, and then you just have pressure is equal to a constant, so that would be our isobaric process, where pressure is constant and it's a flat line. And you could also mathematically have a case where n is less than 0. You might not see it as much, but that would look something like this, where your line curves up and to the right like this. So we know that we are going to have this case, so our line is just going to slope down and to the right, and we can draw in that line right here on the graph, just like this. And then the final touch is to add an arrow indicating the direction of the process. So we know that we are going to draw our arrow pointing from state 1 to state 2. So we start at state 1 up here, and then we'll finish down here. And this is what the final PV diagram should look like.